Hello everyone. So many of you probably heard this term in some popular science lecture that classical forces classical forces arise due to exchange of virtual particles. Okay. So the goal of this lecture is to understand how classical forces arise. The goal today here, how to think about classical forces in the language of quantum field theory. Okay. So we'll try to tell the idea, but so let's consider a very general setting. Consider 2 to 2 scattering. Of the very particular form. So let's say there is a particle phi with momentum k1 plus some particle chi at momentum k2, and this goes to some particle phi at k3 and chi at k4. Okay, so basically something happening here, we don't know what's happening here, but the particle that's entering, so let's say this is my phi particle, and the particle the other, let's say this is my chi particle. So the incoming and the outgoing set of particles are the same apart from at different momentas. Okay, and let's say we know how to compute this scattering amplitude. Okay, we will give some examples, but let's say for the moment that for the sake of generality that this is the scattering we know how to compute this. And the basic idea you can think is that in the non-relativistic limit, we can think one of these particles is creating a background potential and the other particle is being scattered by that potential. I mean, just remember the case of Rutherford scattering. okay, where there was some heavy nucleus sitting here, and then we were throwing electrons, and they were being scattered. So you can think that in this language, in the language of quantum field theory, you can think that this is like my chi particle, some chi, and this is like my phi. Okay, this is the basic idea. So this idea is basically important thing is that in the non-relativistic limit we can think in this way, and if we think in this way, then whether it's a particle, so you can think that Rutherford scattering can be thought in two ways. One is that the phi particle is being scattered by a non-relativistic potential, Coulomb potential, or it can be thought also as a scattering of I mean you are throwing neutron, the nucleus of the heavy atom and the electron, and what's coming out is again nucleus of the heavy atom and electron. Okay, to be very precise, we have to then deal with fermionic particles, but we just considering a more simpler setup where we just scatter some scalar particles. Okay, so then in this setup, first important thing, so in order to take the non-relativistic limit, first important thing is that relativistic and non-relativistic, and non-relativistic normalization of states. Okay, so in relativistic theory, the normalization of state is that, let's say there is a momentum state P and there is a momentum state P prime and P, then they are normalized at 2EP 2 pi cube P minus P prime. So these are the spatial momentas. Whereas in non-relativistic theory, this is simply 2 pi cube, sorry, there is a delta function here, P minus P prime, which roughly means that the relativistic states are roughly speaking 2E times P non-relativistic states. I mean, this is the Hilbert space of non-relativistic quantum mechanics. So this is a vector in the Hilbert's space of non-relativistic QMech, and this is in relativistic theory. Okay, but now in relativistic theory, the leading contribution of energy is roughly speaking, so this is same as 2m mass of the particle plus some small corrections times nr. Okay, so this is the first thing about the relativistic and non-relativistic normalization of state, which will be important for us if we want to consider the scattering. Okay, now let's say Let's consider the non-relativistic scattering first. So in this case, you can show that the non-relativistic scattering of two states due to some potential. Okay, so the transfer element due to some potential is same as I V tilde Q delta final energy minus initial energy, and then D3 PF minus PI minus Q. So this is the momentum transfer due from the potential. Okay, but now let's now consider the similar thing in relativistic theory. So in relativistic theory, the scattering, so this is in relativistic theory, the scattering, we write it as some m q, the momentum transfer again, and then there are some energy conserving delta functions. Okay, but now let's now take the non-relativistic limit of this relativistic answer. Okay, then comparing these two things, comparing this formula with this formula, along with the non-relativistic normalization of state, it basically becomes then that the V tilde of Q is same as minus the non-relativistic limit of relativistic scattering over m phi m chi. Okay, so this is a very important formula. This is an expression of the for the potential in terms of relativistic scattering. Okay, so we will repeatedly use this formula and then we will try to derive results out of it. Okay, here before we go into the explicit computations, we just write one result. Okay, so firstly note that this is a potential, this is the Fourier transform of the potential. So whatever these things gives, it gives a Fourier transform of the potential. So we want the real, the real space potential in terms of the space-time coordinates. Okay, so in order to do that, we actually have to Fourier transform. So So then V of x will be obtained by d3q by 2 pi q v tilde q exponential I q dot x. Okay, and later you will find that in many cases, in almost all the cases, we'll get some potential which is of the roughly of the form 1 over q square plus some m square. Okay, and we just write this result because we will be using this result again and again, the Fourier transform of this. So at this point it's just an ad hoc mathematical computation, but you will later see that what its utility is. So this is same as this. You can do the Fourier transform. In the note it is given, it just becomes 1 over 4 pi 1 over r exponential minus mr. Okay, in particular in the mass goes to 0 limit, this just becomes this just becomes 1 over r basically. Okay. So let's now try to do some simple computations. So first we will we will find the expression for the Coulomb law, and in relativistic theory it will happen due to mass exchange of massless spin 1 particle. Okay, so in order to do that, what we do, we consider two charge scalars. So we take two charge scalars and we compute the scattering due to exchange of spin. So this is spin 1. I forgot to mention the arrows. Okay, this scattering amplitude is easily computable, and this scattering amplitude simply becomes, I mean, we have done it. This becomes E of, so this is my particle phi, this is my particle psi, so this just becomes E phi E psi. Okay, this is also K1, this is K2, and this is K3, this is K4. Then this just becomes this K1 plus K3 mu eta mu nu K2 plus K4 nu over Q square. Okay. Now in the non-relativistic limit, energy, so in the non-relativistic limit, we know that energy of a particle is much greater than energy is roughly m square over p square root p square plus m square, and in the non-relativistic limit this is much greater than p. Okay, and what that means that in this expression, so in this expression the eta 00 component dominate. because in the non-relativistic limit, the zeroth component is much greater than the other component. So in that limit, this answer just becomes exponential I e phi e psi m phi m psi 1 over q square. Okay. Then from this formula, we conclude that the potential p tilde of q is just e phi e psi over q square. Okay. Now we can Fourier transform this. And we get the potential v tilde of x, which is just d3 q over 2 pi cube v tilde q exponential I q dot x to be simply e phi e psi over 4 pi r. So this is Coulomb's law. Okay. In the same way, one can consider scattering of particles due to exchange of massless spin 2. Okay. So now we do the same computation. We do very similar computation. Okay, I actually forgot to write down. So this vertex has E phi and this vertex has E psi. That's why this formula came. So now we have considered a very similar formula, but in this case, we have now considered the exchange of massless spin 2. Okay, so this now in this case, one unique thing is that in the vertex factor for both of these, so if I write the vertex factor to be k phi and this to be k psi, then there is a beautiful theorem by Weinberg which showed that from consistency of the quantum theory, these two things has to be same. This implies that the scattering amplitude, actually I gave the computation details. In the scattering amplitude, in the non-relativistic limit, so in the scattering amplitude again becomes, so the scattering amplitude is something like, it's very similar to the above. Again, let me write the basic points. So this is spin 2. So massless spin 2 propagator has two metric tensors. Okay, and again in the non-relativistic limit, eta 0 component dominate. And in that limit, the scattering amplitude just becomes this implies that the potential and then from then we can Fourier transform again. And we get V tilde of x, the potential is simply minus kappa square m pi m psi over 8 pi 1 over r. So first note one important difference, that this was a plus sign, positive, whereas this is a negative quantity, minus sign. Secondly, note that the coupling constant that appears here is k square, which means that it's always universally attractive. Whereas here the thing that appears is a combination of E phi and E psi, and both of them can have any sign. And since because of this it can be attractive or can be repulsive. In gravity this is not allowed because of this condition. I mean, because if this condition was not there, then the gravity amplitude also you would have got is some k phi times k psi. But what happens in gravitation is that because which comes up unitarity, that these two things has to be same, and we wrote this same as kappa. Okay, so this is another thing, that the force, the classical force, that arise due to massless spin 2 is universally attractive. So this is actually part of a more general statement which one can find in Feynman lecture of gravitation. That let n be an integer, let n be a non-negative integer. Then spin 2n plus 1 exchange, which means odd spin exchange, can give rise to both attractive and repulsive force. Okay, whereas even spin exchange, spin 2n exchange, even spin exchange can give rise to only attractive force. It's a very interesting statement. I encourage, so firstly you can you can easily show it for spin 0 exchange. But for the more general statement, we do not prove it in this lecture, but I encourage the students to think about it and try to prove this. Okay, and this shows how classical forces arise due to due to exchange of virtual particles. Okay, so note that the first part of the lecture where we related these this formula of the potential with the non-relativistic limit of the scattering. This formula is very general and it's true for uh, any non-relativistic scattering. For example, you can also consider loop correction to the right hand side, and you can also ask the question that what happens, how the classical potential is corrected due to loops in quantum field theory. Okay, so this concludes our discussion on the relation between classical force due to virtual exchanges.